Right now, at the very edge of the observable universe, there are galaxies that should not exist. Not in the sense that they are unusual, not in the sense that they are rare or surprising or outside the expected range. In the sense that the most successful scientific model humanity has ever constructed, a model tested against more data, refined by more minds, and confirmed by more independent measurements than almost any theory in the history of science, says these galaxies cannot be there. Cannot. The model does not predict them. The model forbids them. And yet there they are, measured, confirmed, published in peer-reviewed literature, and multiplying with every new observation. There are more of them than there were a year ago. There will be more still by the time you finish listening to this. You feel nothing unusual right now. The room around you is the same room it was a moment ago. Whatever surface you are lying on has not shifted. Your body is still. But the fact that those galaxies exist, the fact that they have been found and cannot be explained away, means that something about the story we have been telling ourselves, about the universe, about how it began and how it grew and what it is made of, is wrong. Not slightly wrong. Not wrong at the margins, in a way that a small adjustment will fix. Wrong in a way that physicists are beginning to describe using a word they almost never use. They are calling it a crisis. This is not speculation. This is what the data says. And the data is coming from the most powerful space telescope ever built. If this is the kind of investigation that interests you, subscribe now. Because what we are about to go into is not one impossible thing. It is two, and they may be connected. And together, they suggest that our understanding of the universe, the picture we assembled across a century of work, the model that predicted the temperature of the leftover radiation from the Big Bang to 4 decimal places, may be missing something enormous, something that has been there all along, hidden in the math, waiting for a telescope precise enough to reveal the contradiction. The investigation starts here. To understand what is happening at the edge of the universe, you have to first understand what we thought was happening. Not in a vague, hand-waving way, in the specific, precise way that scientists mean when they say they have a model. Because the model that is now in trouble is not a rough sketch, it is one of the finest intellectual achievements in human history. And if it is wrong, even partially wrong, then what replaces it has to be even better. And that is interesting, not frightening, interesting. The story begins in 1929. Edwin Hubble, working with the 100-inch telescope at Mount Wilson Observatory in the hills above Los Angeles, published a paper that would permanently alter humanity's understanding of its place in the cosmos. He had been measuring the light from distant nebulae, objects that had been debated for years as to whether they were nearby clouds of gas inside our own galaxy or entire galaxies in their own right, each containing hundreds of billions of stars, each separated from us by distances that made the numbers almost meaningless to write down. Hubble's earlier work had settled that debate. The nebulae were other galaxies. The universe was vastly larger than anyone had thought. But what Hubble noticed in 1929 was something different. He had been measuring not just the distances to these galaxies, but also their velocities, how fast they were moving, and in what direction. And what he found, when he plotted the data, was a pattern so clean and so unexpected that it required a complete reimagining of what the universe was. Every galaxy he could measure was moving away from us. Not just one or two, not just most of them, every single one. And the relationship between distance and velocity was strikingly simple. The farther away a galaxy was, the faster it was receding. Double the distance, roughly double the speed. The relationship was linear. This single observation implied something almost too large to hold in the mind at once. The universe was expanding, not in the sense that galaxies were flying outward through static empty space, like debris from an explosion. The space between them was stretching. The fabric of the universe itself was growing. Every point in the universe was moving away from every other point. The way dots drawn on the surface of a balloon move away from each other as the balloon is inflated, not because the dots are moving on the surface, but because the surface itself is growing. From the perspective of any one dot, all the other dots appear to be receding, and the ones that were already farther away appear to be receding faster, simply because there is more surface between them that is growing. If you ran time backward, if you compressed that expansion, reversed it, shrunk all the distances, galaxies would draw together. The universe would become denser and hotter. Go back far enough and everything you can see or detect or imagine, every galaxy, every star, every atom, every particle of matter and energy in the entire observable universe would converge on a single point of inconceivable density and temperature. This was the Big Bang, not confirmed in 1929, but implied by it. The math pointed toward a beginning, a moment when time and space themselves came into being, when the laws of physics as we understand them began to operate, and from which everything you have ever known has been expanding and cooling and structuring itself ever since. The confirmation came in 1965, when Arno Penzias and Robert Wilson, working at Bell Labs in Holmdel, New Jersey, picked up a strange, persistent hiss in their radio antenna. They were not looking for cosmological signals. They were calibrating the antenna for a communications project. The hiss was coming from everywhere at once, not from a specific direction, not from a specific source, from every direction in the sky at the same intensity, no matter where they pointed the instrument. They initially thought it was noise from the equipment itself. They checked the electronics, they checked the connections, they found pigeons nesting inside the horn-shaped antenna, and they cleaned out what they very carefully described as a white dielectric material coating the interior surfaces. They removed the pigeons. They cleaned everything they could think to clean. The hiss remained. What they had found was the cosmic microwave background. The leftover heat from the Big Bang itself cooled over 13.8 billion years of expansion to a temperature just 2.725 degrees above absolute zero, and filling the entire sky with a faint, uniform glow of ancient radiation. It was the most direct evidence possible for a hot, dense, early universe. The universe had once been a plasma of charged particles and radiation so hot and dense that light could not travel freely through it. As it expanded and cooled, at a moment about 380,000 years after the Big Bang, the plasma settled into neutral atoms, and the universe became transparent for the first time. The light that was released at that instant has been travelling ever since, cooling and stretching. That is what Penzias and Wilson detected. Penzias and Wilson won the Nobel Prize in 1978. The Big Bang model became, from that point on, the foundation of cosmology. Over the following decades, the model was refined, tested, and extended in ways that seemed to confirm it at every turn. In the 1970s, astronomers studying the rotation curves of spiral galaxies found something they could not explain. Galaxies rotate like pinwheels, with the stars in the outer regions orbiting the galactic center. Under Newtonian gravity, the stars at the edge should orbit more slowly than the stars near the center, the same way the outer planets of our solar system orbit the Sun more slowly than the inner ones. But that is not what the observations showed. The outer stars were moving just as fast as the inner ones. The rotation curves were flat when they should be falling. The only explanation that worked was that there was more mass in these galaxies than could be accounted for by the visible stars. A great deal more. Not a small correction, not a factor of 2, a factor of 5 or 6, or in some cases more. There had to be an enormous halo of matter surrounding these galaxies, matter that exerted gravity but emitted no light. This was called dark matter. The evidence for dark matter has since accumulated from dozens of independent lines of observation. The gravitational lensing of light by galaxy clusters, the the temperature distribution of hot gas in those clusters, the structure of the cosmic microwave background, the large-scale distribution of galaxies across the sky. All of them point to the same conclusion and the same approximate fraction. The universe is made of about 27% dark matter. We do not know what it is, but we know it is there because of what it does. Then came the discovery that changed everything again. In 1998, two independent teams studying the brightness of distant supernova, exploding stars whose intrinsic luminosity is known well enough to be used as standard candles, measuring distance from how bright they appear, made a discovery that none of them had been expecting to find. They had gone into the project expecting to measure the rate at which the expansion of the universe was slowing down. Gravity should be pulling matter together. The expansion should be decelerating. The question was, by how much? What they found was that the expansion was not slowing down. It was speeding up. The distant supernovae were dimmer than they should have been, which meant they were farther away than a decelerating universe would predict, which meant the universe was expanding faster than it had been in the past. Some form of energy was pushing space apart, counteracting gravity, accelerating the expansion from within. They called it dark energy. It won the Nobel Prize in 2011. The universe it implied was one in which ordinary matter, the stuff that makes up stars, planets, people, everything you have ever seen or touched, constitutes only about 5% of the total energy content. Dark matter makes up about 27%, and dark energy makes up the remaining 68%. 68% of the universe is something no one has ever detected directly, something that appears to act like a property of space itself, a pressure that pushes outward at a rate that does not dilute as the universe grows. The resulting model is called lambda CDM. Lambda represents the cosmological constant, the term in Einstein's field, equations that encodes dark energy. CDM stands for cold dark matter. It is the standard model of cosmology. And for roughly 2 decades, it was one of the most successful scientific models ever constructed. It predicted the pattern of temperature fluctuations in the cosmic microwave background with extraordinary precision. It predicted the large-scale structure of the universe, the vast web of galaxy filaments, sheets and voids that maps at the grandest scale like the internal architecture of a vast biological organism. It predicted the rate at which galaxy clusters form as a function of time. It predicted the ratio of hydrogen to helium in the universe from nucleosynthesis in the first 3 minutes after the Big Bang, consistent with what we observe. It was, in every test anyone could devise, correct. But it made one set of predictions that has now been tested with an instrument no one had when the model was being built. It predicted, with specific precision, what the earliest galaxies in the universe should look like. And it is those predictions that are now in serious trouble. The James Webb Space Telescope launched on Christmas Day, 2021. It was the product of more than 25 years of planning, design, engineering, failure, recovery, and refinement. The program nearly died multiple times, from budget overruns, from technical setbacks, from congressional threats to cancel it entirely. More than 100,000 people contributed to it at various points across its decades of development. It cost approximately $10 billion, and when it launched on an Ariane 5 rocket from the Guiana Space Center in Kourou, French Guiana, it carried with it the most concentrated set of scientific expectations in the history of space astronomy. Webb is positioned at the second Lagrange point, about 1.5 million kilometers from Earth, in the direction away from the Sun, where the gravitational pulls of the Earth and Sun balance in a way that keeps it in a stable configuration without consuming large amounts of fuel. It sits in permanent darkness, shielded from the Sun's heat by a 5-layered sun shield the size of a tennis court. The cold of space on Webb's observing side reaches approximately -233 degrees Celsius. that extreme cold is necessary. Webb detects infrared light, heat radiation, and to do that reliably, the telescope itself has to be colder than almost anything it is trying to observe. The mirror is made of 18 hexagonal segments of beryllium, a metal chosen for its rigidity at cryogenic temperatures and its low weight, coated with a microscopically thin layer of gold. Each segment is roughly the size of a coffee table. Together, they form a primary mirror 6.5 meters across. That is 2.5 times the diameter of the Hubble Space Telescope's primary mirror. The area difference is more dramatic. Webb collects about 6 times as much light. And light collection is everything in observational astronomy. More light means you can see fainter objects. Fainter objects means more distant objects. More distant objects means further back in time. The extra size is only part of the story. The critical part is what wavelengths of light Webb is designed to detect. As the universe expands, the light travelling through it is stretched. The wavelength of that light grows longer, as space itself grows. Light that was originally emitted as visible light or as ultraviolet light arrives at our telescopes shifted toward the red end of the spectrum. This is called redshift. It is directly proportional to distance. The farther away a galaxy is, the longer its light has been travelling through expanding space, and the more its wavelength has been stretched. For the most distant galaxies we can observe, the ones seen as they appeared only a few 100 million years after the Big Bang, the light has been stretched so dramatically that it arrives not as visible light at all, but as infrared radiation. Hubble, designed primarily for visible and near-ultraviolet light, could barely detect these objects. Webb, built specifically for infrared, can see them clearly. Not just detect them, analyze them in detail, break their light into its component wavelengths, identify the chemical fingerprints of specific elements in their gas, measure their velocity, their temperature, their stellar populations, and the mass of the black holes at their centers. What Hubble could barely see, Webb can read. What Webb began reading in its first year of operation was not what the standard model had predicted would be there. The first strong hints came in late 2022, a few months after Webb began releasing science data. Astronomers conducting deep field observations, long exposures of tiny patches of sky, collecting photons from sources billions of light years away, noticed galaxies in their images that appeared, from their colours, to be at extraordinary distances. Their light was deeply redshifted into the infrared, suggesting they were being seen as they appeared less than 1 billion years after the Big Bang. These were not the first distant galaxies ever detected. Hubble had found galaxies at high redshift. What was different was how many there appeared to be in Webb's images, how bright they were, and what their brightness implied about their mass. Under the lambda-CDM model, galaxies in the early universe should be small and relatively dim. The reasoning is based on physics that is not optional. It follows directly from the rules of how structure forms in an expanding universe seeded with dark matter. In the first moments after the Big Bang, matter is distributed almost uniformly. There are tiny density variations, perhaps 1 part in 100,000, seeded by quantum fluctuations in the earliest instance of cosmic time that were subsequently stretched to cosmic scales by a period of extremely rapid expansion called inflation. These tiny density variations are real. They are the fluctuations visible in the cosmic microwave background, temperature differences of about 30 millionths of a degree across the sky. They are the seeds of everything we see, the seeds of galaxies, galaxy clusters, and the entire large-scale structure of the cosmos. Gravity amplifies these seeds. The slightly denser regions attract more matter, which makes them denser still, which attracts more matter. Dark matter halos form first, gravity wells that grow hierarchically. Small halos merging into larger halos merging into still larger ones. Ordinary matter falls into these halos, cools by radiating energy away, compresses, and eventually reaches the density required to ignite nuclear fusion. Stars light up, galaxies begin to take shape. This process takes time. There are physical limits to how fast it can proceed. The universe has only expanded by a certain amount. The dark matter halos have only had a finite time to grow. The amount of gas available to cool and form stars is constrained by the total baryon density of the universe, the number of protons and neutrons per unit volume, which is itself precisely measured from the cosmic microwave background and cannot be changed after the fact. Even in the most favourable corner of the model's parameter space, the densest possible region, the fastest possible cooling, the most efficient possible star formation, you cannot produce a galaxy above a certain mass within the first 700 million years of cosmic history. The model sets a ceiling. It is not a soft recommendation. It is a hard limit derived from the physics of structure formation. Some of the galaxies Webb found appear to violate that limit. The word appeared is carrying real scientific weight there. In late 2022 and early 2023, many of the initial candidate galaxies had photometric redshifts, meaning the redshift was inferred from the color of the galaxy across several broadband infrared filters, rather than from the direct measurement of specific spectral lines. Photometric redshifts can be wrong. A galaxy that looks very red might be extremely distant and redshifted, or it might be a nearby dusty galaxy. The two can look similar in broadband images. A photometric redshift is a probability estimate, not a confirmed measurement. But spectroscopic observations followed, and then more spectroscopic observations. Spectroscopy breaks the light from a galaxy into its individual wavelengths with much finer resolution, and looks for specific emission or absorption lines, the spectral fingerprints of particular elements at particular temperatures that appear at predictable wavelengths. When those lines are found at shifted wavelengths, the redshift is determined exactly. The galaxy is placed at a precise distance. The measurement is confirmed, and in case after case, the spectroscopic confirmations showed that the photometric estimates were right. These galaxies were where their colours said they were. They were as luminous and therefore as massive as the brightness implied. They were being observed as they appeared in the first few 100 million years of cosmic history, and they were far too large for that time. One of the pivotal papers in this story was published in Nature in early 2023, led by Ivo Labbé at Swinburne University of Technology in Melbourne, Australia. It identified 6 candidate galaxies that, if the mass estimates were accurate, each contained between 10 billion and 100 billion solar masses in stars. 10 billion solar masses. To give that number the moment it requires, the Sun is 1 solar mass. The Milky Way, our entire galaxy, contains somewhere between 200 and 400 billion solar masses in stars. These early galaxies, seen when the universe was between 500 and 800 million years old, had already accumulated a significant fraction of the Milky Way's entire stellar mass in far less time than should have been physically possible. Labbé and his colleagues compared these candidates to the predictions of the best available lambda-CDM simulations, not rough estimates, but the most sophisticated computer models of cosmic structure formation that exist running on some of the largest supercomputers in the world. The simulations across millions of simulated cubic megaparsecs of universe did not produce galaxies of that mass at those epochs, not in small numbers, not rarely, not at all. The observed candidates would have been cosmic impossibilities in the simulated universe. Labbé told journalists that if the objects were real, they should not exist, that if even a fraction of the candidates were confirmed at their estimated masses, the standard model would need to be substantially revised. Other researchers were appropriately cautious. Science is cautious by design. Some pointed out that the mass estimates relied on assumptions about the stellar populations inside the galaxies. Assumptions about how many young stars versus old stars were present, and what fraction of the light was coming from stars versus from the active nucleus of the galaxy. These assumptions could be wrong. The mass estimates could be too high. This caution was productive. Over the following year, careful analysis revised some of the initial mass estimates downward. Several of the most extreme candidates turned out, on closer examination, to contain luminous, active galactic nuclei, feeding supermassive black holes whose brilliance had been mistaken for stellar emission. Remove the nuclear contribution from the light budget and the stellar mass drops significantly. Other candidates held up under scrutiny, and others were found. New candidates were identified. The final picture, after a year of careful analysis by multiple independent teams, was more moderate than the initial reports, but still deeply challenging to the standard model. A significant population of massive early galaxies remained, not at the most extreme initial estimates, but at levels that exceed the predictions of lambda CDM by a factor of 10 or more in certain mass ranges at certain redshifts. That is not measurement noise. That is not within the error bars of any reasonable version of the standard model. It is a real anomaly, confirmed by multiple teams, confirmed spectroscopically, confirmed with multiple analysis methods. There is one specific galaxy worth naming here, because it illustrates the problem with particular clarity. JADES-GES-Z13-0. It was identified as part of the JWST Advanced Deep Extragalactic Survey, JADES, one of the most ambitious observation programs Webb is running. It has a spectroscopically confirmed redshift of 13.2. That number deserves a pause before you move past it. A redshift of 13.2 means that the wavelength of the light from this galaxy has been stretched to 14.2 times its original length during its journey through expanding space. It means the light left this galaxy when the universe was approximately 320 million years old. The universe is currently 13.8 billion years old. We are seeing this galaxy as it appeared when the universe was 2.3% of its current age. If the universe's entire history were compressed into a single calendar year, this galaxy was photographed on the 3rd day of January. And yet it is there, formed, glowing, containing stars that had already lived and burned for millions of years. JADES-GS-Z13-0 is not the most extreme outlier in terms of stellar mass. But it was, at the time of its confirmation, the most distant galaxy ever confirmed by spectroscopy. It was a record that stood for months before Webb pushed further still. And what it demonstrates, what the full population of Webb's early galaxy detections demonstrates, is that the universe was building structure more quickly than anyone expected at the very earliest times. The star formation machinery was running in the first hundreds of millions of years after the Big Bang at a pace that our models said should not have been physically possible. This is established. This is measured. This is not inference or extrapolation. It is in the data. So, galaxies that are too big, too bright, too mature, too soon. That is the first impossible thing. The second one has been accumulating evidence for longer, has a higher statistical significance, and may be more fundamentally threatening to the standard model. It is called the Hubble tension. The Hubble constant, written as h0 or h0, is the rate at which the universe is currently expanding. It is measured in kilometers per second per megaparsec. A megaparsec is approximately 3.26 million light-years, roughly the distance between the Milky Way and the Andromeda Galaxy. The Hubble constant tells you how fast any 2 points in the universe are moving apart from each other per unit distance between them. It is not a peripheral number. It is the central number of cosmology, the parameter on which the age of the universe, the size of the observable universe, and the entire timeline of cosmic history depend. There are two completely independent methods for measuring the Hubble constant. Each uses fundamentally different physics. Each has been developed and refined by separate research communities over decades. Each produces a precise, internally consistent result. And the two results disagree. The first method uses the early universe, specifically the cosmic microwave background. The CMB is not just a uniform glow, it has structure. Tiny temperature variations at the level of 30 millionths of a degree are distributed across the sky in a pattern that is not random. It was produced by sound waves, oscillations in the hot plasma of the early universe, rippling through a medium of charged particles and radiation in the first 380,000 years of cosmic history. These oscillations have a characteristic scale. The distance sound could travel in the early universe before the plasma cooled and the universe became transparent. This distance, the sound horizon, is calculable from the known physics of the early plasma, and it leaves a specific imprint in the pattern of CMB temperature fluctuations. By measuring that pattern with sufficient precision, you can extract the Hubble constant. The Planck satellite, a European Space Agency mission that mapped the CMB from 2009 to 2013, made this measurement with extraordinary care. It found a Hubble constant of approximately 67.4 kilometers per second per megaparsec. The uncertainty on that measurement is less than 1%. That is the most precise measurement of the Hubble constant from the early universe we have ever made. It is consistent with every other parameter of lambda CDM. The second method uses the modern nearby universe, specifically a chain of overlapping distance measurements called the cosmic distance ladder. At the base of the ladder is parallax, the direct geometric measurement of distances to nearby stars by observing the tiny shift in their apparent position as Earth moves around the Sun over 6 months. This works for stars within a few thousand light years. One step up the ladder are Cepheid variable stars, pulsating stars whose brightness oscillates with a precise period directly related to their absolute luminosity. By calibrating Cepheids locally using parallax, you can use them to measure distances to galaxies tens of millions of light years away. One step above Cepheids are Type 1a supernovae, the exploding stars used in the 1998 dark energy discovery, which reach a characteristic peak luminosity that makes them identifiable at distances of billions of light years. This ladder, when climbed carefully, gives you the expansion rate of the nearby universe, unconstrained by assumptions about the early universe or about the physics of lambda CDM. It measures what the expansion rate actually is today, through direct observation rather than through model-dependent inference. The SHOES project, Supernovae HO for the equation of state, has spent more than a decade climbing this ladder. It is led by Adam Rees at Johns Hopkins University, who shared the Nobel Prize in 2011 for the original discovery of dark energy using supernova. His team has calibrated the distance ladder at every rung, checked the Cepheid measurements in multiple galaxies, refined the supernova sample, and used Webb to extend the precision of the nearby calibrations in ways that Hubble could not achieve. Their value for the Hubble constant after all of this work is approximately 73 kilometers per second per megaparsec. 73 versus 67.4. The difference is 5.6 kilometers per second per megaparsec. In terms of the universe's expansion rate, that is an 8% discrepancy. In terms of statistical significance, accounting for the uncertainty in each measurement, the disagreement currently sits at more than 5 sigma. 5 sigma is the threshold that physicists use to claim a discovery. It means that if both measurements are correct, and the difference is due purely to statistical fluctuation, the probability of that happening by chance is less than 1 in 3.5 million. You cannot dismiss a 5 sigma tension as noise. And here is what makes it more serious. The tension has not shrunk with time. Every major new analysis, every time the SHOES team adds new data, every time the Planck team refines its analysis, the numbers have stayed where they are. 73, 67.4. For more than a decade, both measurements have been getting more precise and both have been staying the same. This is not the behavior of a measurement error. Measurement errors, when you add more data and improve your methods, tend to shift or resolve. This one is not resolving, it is sharpening. There is a third measurement that adds nuance to the picture. Wendy Friedman at the University of Chicago leads a team using a different set of standard candles. The tip of the red giant branch, a sharp luminosity feature that appears at the end of a red giant star's life and has a characteristic brightness that can be used to measure distances. Her team also uses Webb for calibration. Their result sits at approximately 69 to 70 kilometers per second per megaparsec. This sits between the Planck value and the SHOES value. Friedman argues that the disagreement between her result and Planck's does not reach the level that requires new physics, that improved calibrations could close the remaining gap. Rees argues that his result, at 73, clearly requires something beyond the standard model. This disagreement between two world-class measurement programs is not a failure of science. It is science in progress. It means the systematic errors in the distance ladder are not yet fully mapped. But it does not mean the tension will go away. It means the debate is about the magnitude of the discrepancy, not about whether it exists. Both Friedman and Rees find a Hubble constant higher than Planck's 67.4. The question is how much higher, and whether the difference requires new physics or merely better calibration. Most of the physics community believes the answer will require new physics. The reasons are worth understanding in detail because they illuminate how deeply the two numbers are in conflict. If the Planck number is right, if the Hubble constant really is 67.4, then the distance ladder must contain a systematic error large enough to push the measured value from 67.4 to 73. That error would have to be present in Cepheid measurements, or in the supernova sample, or in both. It would have to be systematic, not random, but consistently in the same direction, and large enough to shift the result by 8%. Researchers have been searching for such an error for years. They have checked Cepheid measurements in different environments at different metallicities using multiple instruments, including Webb. They have checked the supernova sample for selection effects, for calibration errors, for environmental biases. They have checked the Cepheid calibration using completely independent methods, including the tip of the red giant branch and carbon star luminosity measurements. The systematic error, if it exists, has not been found. If the SHOES number is right, if the Hubble constant really is 73, then the early universe, as described by lambda CDM, produces a CMB pattern that implies a different expansion rate than the universe actually has, which means lambda CDM is wrong about something in the early universe. Something between the era of the CMB and today changed the expansion rate in a way the model does not account for. That something is new physics. There is a third option, that both measurements are correct, but both contain systematic errors that happen to push them in opposite directions. That would be an extraordinarily unfortunate coincidence. It cannot be ruled out. But as the precision of both measurements has improved, the coincidence required to explain the discrepancy has become larger. It is becoming an increasingly uncomfortable position to maintain. What has theorists genuinely excited and genuinely unsettled is the possibility that the two anomalies we have discussed are connected. The impossible early galaxies and the Hubble tension both involve the same quantity, the early expansion rate of the universe. How fast the universe was expanding in its first billion years determines how quickly dark matter halos could form, how quickly galaxies could grow, and what the Planck satellite measures when it analyses the cosmic microwave background. A modification to the early expansion rate affects everything. The problem is that any modification to the early expansion rate that solves the Hubble tension, that shifts the CMB inferred Hubble constant up towards 73, tends to suppress early structure formation. If the universe was expanding faster in its early epochs, matter had less time to cluster before the expansion pulled it apart. The impossible galaxies would become more impossible, not less. You would expect fewer large early galaxies when the data shows more. The two anomalies point in opposite directions within the standard framework of solutions. Unless the modification is not simply a higher expansion rate, but a more complex change in the early universe's content or evolution, something that changes both the expansion history and the efficiency of structure formation simultaneously in a way that brings both observations into agreement. This would require something more subtle than just adding a period of extra dark energy. It might require modifying the properties of dark matter, or changing the initial conditions of the universe, or invoking physics that we have not yet incorporated into any model. The theorists working on this problem are not short of ideas. They are short of observations precise enough to distinguish between the ideas. That is the constraint. There are dozens of models on the table. Most of them fit the current data reasonably well, because the current data does not yet have the precision to rule them out. What is needed is more data, at higher precision, across more observational probes simultaneously. Let us spend some time on the specific models that theorists have proposed, because the variety of what is on the table is itself instructive about the depth of the problem. Early dark energy is the most discussed proposal for solving the Hubble tension. In this model, there is an additional form of dark energy, different from the cosmological constant, that was present in the very early universe, before the time of the CMB, and that then decayed away. This early dark energy increases the expansion rate in the pre-CMB epoch, which changes the scale of the sound horizon, which shifts the Hubble constant that Planck extracts from the CMB data. If the sound horizon is smaller than lambda CDM predicts, the inferred Hubble constant comes out higher. Early dark energy makes it smaller by speeding up the early expansion. The specific form of early dark energy that has been studied most carefully is a scalar field, a dynamical field that fills space with an energy density that behaves like a cosmological constant at early times before decaying away as the universe cools. It is not an arbitrary construction. There are well-motivated theoretical frameworks from particle physics that naturally produce scalar fields with this behavior related to the physics of inflation and of dark energy itself. The problem, as noted earlier, is that early dark energy also suppresses the growth of structure. It shifts sigma-8, the amplitude of matter clustering, in the wrong direction, making the universe slightly smoother at late times than lambda CDM predicts, when some observations already suggest the universe is slightly smoother than lambda CDM predicts. Adding early dark energy tends to make this separate tension worse. It resolves one problem while exacerbating another. There are modified versions of early dark energy that try to address this by having the field interact with other components of the universe, with dark matter, or with neutrinos, or with a second scalar field. These interactions can change the structure formation history in ways that partially mitigate the suppression of growth. But they introduce additional parameters and additional tuning, which is scientifically uncomfortable. The best theories make predictions with a minimum of 3 parameters. Every added parameter is a place where the model can be adjusted to fit the data without genuinely explaining it. A second class of model modifies dark matter. Standard cold dark matter, particles moving slowly, clustering in a specific hierarchical pattern, produces a universe that looks broadly like the one we observe. But the agreement is not perfect, even in the standard model. Lambda CDM famously predicts more small-scale structure than we observe, more dwarf galaxies around the Milky Way, more compact central density profiles in galaxy halos, problems that have been known for decades and that have been partially addressed by invoking astrophysical feedback processes, but not fully resolved. Some modifications to dark matter would change the formation of early massive galaxies. If dark matter particles interact with photons or neutrinos in the early universe, they stream out of dense regions more efficiently, which modifies the growth of halos. If dark matter decays into a lighter particle over cosmic time, the matter density drops in a way that changes the expansion history and the growth of structure. These effects can be tuned, in principle, to enhance early massive galaxy formation, while leaving the large-scale structure intact. But finding a specific model that does this while also solving the Hubble tension and remaining consistent with all other constraints has not yet been achieved. A third direction is to revisit the initial conditions of the universe, the spectrum of density fluctuations that inflation produced. Standard inflation predicts an almost scale-invariant spectrum, fluctuations of roughly the same amplitude at all scales, with a very slight tilt. This tilt has been measured in the CMB, but the standard spectrum is a prediction of the simplest inflationary models. More complex inflationary scenarios can produce features in the power spectrum, bumps, tilts, or oscillations at specific scales that would enhance structure formation at early times while leaving the CMB largely unchanged. Such features could, in principle, allow more rapid early galaxy growth without obviously violating other observational constraints. This is speculative. There is no confirmed feature in the primordial power spectrum. But the CMB data does contain hints of possible features at specific angular scales, deviations from the best fit simple spectrum that have been reported by multiple analysis teams, but never confirmed at high statistical significance. Webb's observations of early galaxies place a new kind of constraint on the primordial power spectrum at small scales, scales that the CMB cannot probe directly because they were washed out by the thermal history of the early universe. If the impossible early galaxies are real, they effectively require an enhancement of power at the small scales relevant for their formation. This is a new and direct constraint on the theory of inflation, coming from observations of the most distant galaxies Webb can see. That connection between the James Webb Space Telescope and the theory of inflation, the event that set the initial conditions for the entire subsequent history of the universe, is one of the more remarkable aspects of the current situation. A telescope designed to study galaxy formation is, in practice, providing new information about the first fraction of a second of cosmic history. That is the kind of reach that science has occasionally achieved, and always with important consequences. There is a final class of proposed modification that is the most radical of all, and that the most conservative cosmologists still resist, but that a growing number take seriously. It is the possibility that general relativity, the theory of gravity published by Einstein in 1915 and tested in almost every imaginable way since, is not the complete description of gravity on cosmological scales. That the equations that govern how space and time respond to the presence of matter and energy may need to be modified when applied to the very largest distances and the very longest timescales. General relativity has been tested extraordinarily well in specific regimes. In the solar system, in binary pulsar systems, in the detection of gravitational waves from merging black holes and neutron stars, in the behavior of strong gravitational lensing around galaxy clusters. All of these tests involve relatively small patches of space-time, even if the objects involved are massive. What has not been tested in the same way is whether general relativity applied to the entire observable universe, across 13 billion years of expansion, continues to be correct without modification. There are entire families of theories that modify general relativity at large scales while reducing to it in the regime where it has been tested. Scalar tensor theories, in which a scalar field couples to gravity and changes its effective strength at cosmological scales. FR theories, in which the geometric description of spacetime includes additional terms that become relevant at low curvatures. Theories with extra dimensions, in which gravity leaks into additional spatial dimensions at large scales, diluting its effective strength. Any of these could, in principle, modify the expansion history of the universe and the growth of structure in ways that address both the Hubble tension and the impossible early galaxies. None of them has been confirmed. All of them make predictions that the coming generation of surveys will test. The combination of Euclid, Rubin, and Roman will measure the growth of structure over the past 10 billion years with enough precision to distinguish between general relativity and its main alternatives at the level of 1 or 2%. If general relativity is failing at cosmological scales, these surveys will find the signature of that failure. If it holds, the modified gravity models will be ruled out. This is also established, not the answer. The answer is unknown. But the fact that the answer will come, and when it will come, and from which instruments, is established. That is a different kind of certainty than knowing the physics. It is methodological certainty. The investigation is structured. The tools are being built. The timelines are known. There is something happening in the field of cosmology right now that does not happen often. Senior scientists, people who have spent their careers working within a framework they helped to build, are openly discussing the possibility that the framework is incomplete in a fundamental way. This is not comfortable for anyone. Lambda CDM represents decades of collective intellectual investment. The model has been spectacularly successful. Saying it might be wrong in a deep way is not a small thing, but that is what the data is forcing. Not demanding, the systematic errors might still exist, the anomalies might be resolved within the existing framework, and Lambda CDM might emerge from this test intact and strengthened. That has happened before in the history of science, and it is not impossible here, but the probability of it shrinks with each new measurement that confirms the tension. When you look at the full picture, the Hubble tension, the impossible galaxies, the sigma-8 tension in matter clustering, the hints from DESI about dark energy that may not be constant, the hemispherical asymmetry in the CMB that no one has yet explained. You see not a single anomaly, but a collection of them. Each one, taken individually, can be addressed with specific explanations. The Hubble tension might be a calibration error in the distance ladder. The impossible galaxies might be explained by extreme star formation efficiency. The sigma-8 tension might be a consequence of baryonic feedback in galaxy formation that simulations have underestimated. Each explanation is individually plausible. But when you ask whether all of them can be explained simultaneously within the existing framework, without any new physics, that is when the problem becomes much harder. The explanations for individual anomalies can conflict with each other. The solution to one tension can exacerbate another. A model that explains the impossible galaxies may worsen the Hubble tension. A model that resolves the Hubble tension may suppress early structure formation. Finding a single coherent set of modifications that addresses all of the anomalies simultaneously without introducing new problems is the challenge that the field now faces. No one has done it yet. There are many candidates in the running. The next decade of data will judge them. Let us be specific about what that next decade holds. The Euclid satellite, launched in July 2023, is now conducting its main survey. It is mapping the shapes and positions of more than 1 billion galaxies out to a redshift of about 2, covering an epoch from about 3 billion years ago to the present. Its primary goals are to measure dark energy and dark matter simultaneously using 2 independent methods: weak gravitational lensing, which measures the slight distortion of galaxy shapes by the intervening distribution of matter, and galaxy clustering, which maps the three-dimensional distribution of galaxies and the Baryon acoustic oscillation scale within it. Euclid will measure the Hubble constant independently of both Planck and the distance ladder, using the Baryon acoustic oscillation scale in the large-scale structure of the modern universe as a standard ruler. Its precision will be sufficient to determine whether the tension between early and late universe measurements is real to beyond 5 sigma, and to constrain the dark energy equation of state to a level that will show whether it is truly constant or varies with time. The Vera C. Rubin Observatory, now in its commissioning phase at Cerro Pachón in Chile, will carry out the legacy survey of space and time for 10 years. Its 8.4-meter mirror and 3,200 megapixel camera, the largest digital camera ever built, will scan the entire visible southern sky every few nights, accumulating a dataset of approximately 20 billion galaxies. The sheer volume of data will allow weak gravitational lensing measurements of the matter distribution with a precision that will either confirm or rule out most of the proposed modifications to dark matter and dark energy. Rubin will also discover millions of supernova and other transient events, extending the supernova Hubble diagram to higher redshifts and improving the calibration of the cosmic distance ladder from an entirely new angle. The Nancy Grace Roman Space Telescope, planned for launch in the late 2020s, will extend Webb's infrared sensitivity across a field of view more than 100 times larger than Webb's narrow angles. This enormous field, combined with Webb-quality infrared sensitivity, will allow statistically significant samples of early massive galaxies to be assembled. Thousands of galaxies across the full range of redshifts and masses where lambda CDM's predictions can be tested systematically. Roman will tell us definitively whether the population of massive early galaxies Webb has found represents a genuine challenge to the standard model, or is a rare outlier explained by sampling variance in a small observed volume. The square-kilometre array, being built simultaneously across South Africa and Western Australia, will be the most sensitive radio observatory in history. Among its scientific goals is the mapping of neutral hydrogen gas, the raw material of star formation, across cosmic history through the 21-centimetre emission line. Hydrogen is the most abundant element in the universe, and tracing it from the epoch of reionization to the present day will provide an independent map of how matter clustering evolved over time. It will also allow an independent measurement of baryon acoustic oscillations in the hydrogen distribution, adding yet another measurement of the expansion history that can be compared to Planck, to the distance ladder, and to Euclid. These instruments are not aspirational projects on a distant horizon. Most are already operating or in final construction. The data they are generating and will generate in the next decade will exceed in volume and precision everything that has been collected in the history of astronomy up to this point. Whatever the universe is hiding in the gap between lambda CDM and the anomalies we are now seeing, it will not remain hidden through this onslaught. The people doing this work are real people. They are at their desks or at their telescopes right now. They are writing code to analyze Euclid's first data releases. They are calibrating Rubin's camera and processing Webb's spectra. They are running simulations on supercomputers, trying different initial conditions, different dark matter models, different dark energy equations of state, testing each against the accumulating observations. Many of them are in their 20s and 30s. They will still be working in 2035 and 2040. They will see the answer. Not all of it. Science does not work that way, but enough. Enough to know whether lambda CDM stands or falls, whether new physics is required, and if so, roughly what shape it takes. You are alive at the moment just before they find out. That is an unusual position to be in. Not better or worse than being alive when the answer is known. just unusual. You are in the moment of tension before the resolution, when the question is fully formed and the investigation is fully underway, but the conclusion has not yet been reached. The impossible galaxies are out there right now, at the edge of what Webb can see, their light having been travelling since before the Sun existed by a factor of 3. The Hubble tension is real, measured at 5 sigma, the best 2 measurement programs in cosmology persistently disagreeing about the most fundamental parameter of the model. Dark energy may or may not be constant. General relativity may or may not be complete at cosmological scales. The initial conditions of the universe, the exact shape of the spectrum of density fluctuations that inflation produced, are being constrained by observations of the most distant galaxies that have ever been seen. All of this is happening simultaneously. All of it is connected in ways that are not yet fully understood. All of it is pushing toward the same conclusion, that the universe is stranger than our best current account of it admits. This is the most interesting thing there is. Not because it involves frightening forces or threatening changes. Nothing about this will affect your life directly. The galaxy JADS-GS-C13-0 does not care about you, and you could not travel there if you wanted to. The Hubble tension does not change anything about the physics governing your daily experience. General relativity, if it turns out to be incomplete at cosmological scales, still works perfectly for every engineering application you will ever encounter. What makes it interesting is something else, something about being a species that can ask these questions and actually get close enough to an answer that the answer talks back. That builds instruments precise enough to measure the temperature of the early universe to 4 decimal places. That can look at a galaxy seen as it appeared 13.5 billion years ago and identify the specific elements in its gas. That can notice from the light of distant exploding stars that the universe is accelerating, and then notice from 2 completely independent measurements of how fast it is accelerating that the 2 measurements disagree, and then spend a decade trying to figure out why. The crack in the most successful scientific model ever built is not a failure. It is the next step. It is what progress looks like. It is a signal from the universe that there is still something left to understand, something significant, something that matters, something that will change the picture when it is found. The telescopes are running, the data is coming, the analysis is underway. And at the edge of the observable universe, in light that has been travelling since before the Earth existed, the answer is already there. Encoded in the brightness and the colour and the spectrum of galaxies that the standard model says should not be able to exist, we are going to read that encoding. We do not yet know what it says, but we are getting close enough to know that it says something new. That is where the investigation stands. That is what is being built to resolve it. And that is what the universe, through the light of its most ancient and impossible structures, is quietly beginning to reveal. There is something that needs to be said about what we mean when we say a scientific model is in crisis. Because that word, crisis, carries a weight in ordinary language that it does not quite carry in scientific usage. In ordinary language, a crisis is an emergency, something requiring immediate action, a situation that cannot be sustained. When we say a scientific model is in crisis, we do not mean any of those things. We mean something more specific and more interesting. Thomas Kuhn, a philosopher of science who spent decades studying how scientific knowledge actually changes, described the structure of scientific revolutions in a book published in 1962. It is one of the most widely read and debated books in the philosophy of science ever written. Kuhn observed that science does not progress in a smooth, linear way, with each new discovery building cleanly on the last. Instead, it proceeds through extended periods of what he called normal science, periods during which a dominant framework, which he called a paradigm, guides research, defines what counts as a valid question, and determines what counts as an acceptable answer. During normal science, anomalies arise, results that do not fit the model, observations that the paradigm cannot account for. Most of the time, anomalies are ignored or explained away or deferred to future investigation. The paradigm is not abandoned at the first sign of a contradictory measurement. It is a framework that has proven its worth across many successful predictions, and one anomalous result does not overturn that track record. But as anomalies accumulate, as they multiply and resist explanation and show up in different measurements by different teams, confidence in the paradigm begins to erode. Researchers begin to spend more of their time on the anomalies and less on the normal problems. Alternative frameworks begin to be proposed and discussed, and eventually, if a new framework is found that explains both the successes of the old paradigm and the anomalies it could not handle, the field transitions. The old paradigm is replaced by a new one. This is a scientific revolution. We do not know whether cosmology is entering a revolution. That is stated clearly and without evasion. It might be that the anomalies we are currently observing, the Hubble tension, the impossible early galaxies, the hints from DESI, are the kind that get resolved within the existing framework. That happened with the apparent anomaly in the abundance of lithium in old stars, which was thought for years to be in conflict with Big Bang nucleosynthesis, and which has been partially addressed through better understanding of stellar physics. It happened with certain apparent tensions in the CMB that looked worrying in early data releases from the WMAP satellite, and were resolved with improved analysis in later Planck data. Normal science has a long history of resolving apparent anomalies without requiring a paradigm shift. But there is something different about the current situation that is worth stating carefully. The Hubble tension is measured at 5 sigma. That is not a preliminary result. It is not a hint. It is a confirmed, reproducible discrepancy between two of the best calibrated measurement programs in the history of observational astronomy, persisting over more than a decade of independent scrutiny, growing stronger rather than weaker as the measurements have been refined. 5 sigma is the level at which the physics community claims discoveries. It is the level at which the Higgs boson was confirmed in 2012. It is not something you explain away with a footnote about calibration uncertainties. And the impossible galaxies, while individually less statistically certain than the Hubble tension, represent a population-level challenge to the standard model. It is not one galaxy in the wrong place. It is dozens, confirmed spectroscopically, appearing at redshifts and with masses that the best simulations of cosmic structure formation consistently fail to produce. Individual galaxy mass estimates carry uncertainty. Population-level statistics do not carry the same uncertainty. When you find that the observed number density of galaxies above a certain mass threshold at a certain redshift exceeds the simulated number density by a factor of 10, the uncertainty in any individual mass estimate is not sufficient to explain the discrepancy. The problem is real. So when cosmologists use the word crisis, they mean this: the anomalies are too significant and too numerous to be comfortable within the existing framework, and no modification to the framework has yet been found that resolves all of them simultaneously without creating new problems. That is a crisis in the scientific sense. It does not mean the sky is falling. It means the investigation has reached a decisive point. The framework is being seriously tested for the first time at its most critical scales with the most capable instruments ever built, and it is showing strain. What comes next, whether the strain is resolved within the existing framework or requires a new one, is the most important question in cosmology right now. Let us go back into the weeds on one specific aspect of this that has not been fully explored, because it is both technically important and genuinely strange. It concerns the nature of dark energy, and specifically what the recent DESI results might mean. Dark energy was discovered in 1998 from the observation that the expansion of the universe is accelerating. The simplest possible explanation for this acceleration is that the vacuum of space has an intrinsic energy density, that empty space is not truly empty, but has a non-zero energy associated with it that remains constant as the universe expands. This is the cosmological constant lambda, and in lambda CDM, it is treated as a fixed property of the universe, unchanged across all of space and all of time. The problem is that we do not know why the cosmological constant has the value it does. When quantum field theory, the mathematical framework that describes subatomic particles with extraordinary precision, is used to calculate the expected energy density of the vacuum, the result is not the observed value. It is larger by a factor of approximately 10 raised to the power of 120. This is not a small discrepancy. It is the largest discrepancy between a theoretical prediction and an experimental measurement in the history of physics by many orders of magnitude. Something cancels the enormous vacuum energy predicted by quantum field theory down to the tiny value we actually observe. We do not know what. We do not know why the cancellation is so nearly perfect, because it is not completely perfect. The cosmological constant is small but not zero. Why it is exactly as small as it is but not zero is one of the deepest unsolved problems in all of physics. This profound theoretical difficulty raises a natural question. What if the cosmological constant is not actually constant? What if dark energy is not a fixed property of the vacuum, but a dynamical field, something that changes over time, perhaps extremely slowly, as the universe expands and cools? In that case, the current value of dark energy would be an accident of the particular epoch of cosmic history we happen to inhabit, and the history of dark energy's evolution would be a new observable that future experiments could detect. The parameterization that theorists typically use to describe this possibility is called the W parameter, or the equation of state of dark energy. For the cosmological constant, W equals -1, exactly. It does not change with time. If dark energy is a dynamical field, W might be different from -1, or it might be -1 today, but have been different in the past, or it might be changing over time. Different values of W produce different expansion histories, different growth rates for cosmic structure, and slightly different patterns in the baryon acoustic oscillation scale as measured at different redshifts. In April 2024, the Dark Energy Spectroscopic Instrument, DESI, released its first year of results. DESI is a spectrograph mounted on the 4-meter Mile telescope at Kitt Peak National Observatory in Arizona, capable of obtaining spectra of 5,000 galaxies simultaneously using a field of optical fibers positioned by robotic actuators. It is the most powerful redshift survey instrument ever built. In its first year, it measured baryon acoustic oscillations at multiple different redshifts, providing snapshots of the expansion history of the universe at different epochs. The results showed a slight statistical preference, not yet at the level of a confirmed detection, but at the level of roughly 3 sigma, for dark energy that is not constant, specifically for a dark energy that was stronger in the recent past than it is today, a model in which the equation of state of dark energy crosses the value of -1 at some point in cosmic history. This is called phantom dark energy, and it would require a form of dark energy that is not simply a scalar field, something more exotic, with unusual quantum properties. 3 sigma is not 5 sigma. It is notable, but not confirmed. When DESI's second year of data is combined with the first year, and when the results are cross-checked against weak lensing surveys from Euclid and Rubin, the significance will either increase or decrease. If it increases, if the preference for dynamic dark energy strengthens with additional data, it would be one of the most significant cosmological discoveries since 1998. It would mean that the cosmological constant is not constant, that the 68% of the universe that we call dark energy is not a fixed property of the vacuum, but a field that evolves over time, with an equation of state that has changed since the Big Bang and will presumably continue to change in the future. This would not by itself resolve the Hubble tension or explain the impossible early galaxies, but it would confirm that the standard cosmological model, which treats dark energy as fixed, is missing something about the dynamics of the universe. And it would open new theoretical territory, new parameters to constrain, new physics to explore. It would be one more piece of evidence that the universe is behaving differently from what the simplest version of the model predicts. It is important to hold all of these threads together at once, because that is what the actual state of the field looks like. Not one clean problem with one clean solution. A web of interconnected measurements, each one adding a constraint, each one potentially in tension with the others, all of them pointing toward a picture that is subtly but importantly different from the standard model. The Hubble tension, the impossible early galaxies, the DESI hint about dynamic dark energy, the sigma 8 tension, the CMB hemispherical asymmetry, the anomalous large-scale peculiar velocities of galaxies. Not all of these are at the same level of significance. Not all of them will turn out to be real, but the fact that they are all present simultaneously, all pointing in a roughly consistent direction, toward a universe whose structure and expansion history do not perfectly match lambda CDM, is not something that should be dismissed. Science has been here before. In the years before Einstein published general relativity, Newtonian mechanics was known to have an anomaly. The precession of Mercury's orbit did not match the prediction by 43 arc-seconds per century. It was a small discrepancy. It had been known for decades. Various explanations had been proposed: an undiscovered inner planet, a distribution of matter near the Sun, a modification to the inverse square law of gravity. None of them worked cleanly. The anomaly persisted unexplained. And then general relativity was published, and the first thing anyone calculated was Mercury's orbit, and the number came out exactly right. The anomaly that had been sitting unsolved for decades was the signature of a deeper theory that the existing framework could not access. We do not know if cosmology is in an analogous position. We do not know if the Hubble tension and the impossible galaxies are Mercury's orbit, the small persistent anomaly that will eventually point directly to the deeper theory. We do not know what the deeper theory would be, but the analogy is not frivolous. It is the kind of situation that scientific history says we should take seriously. There is one more aspect of this investigation that deserves attention: the people who are doing it and the specific human scale of what they are attempting. Adam Rees has spent more than 20 years measuring the expansion rate of the universe. He began as a graduate student, worked on the supernova survey that discovered dark energy, won the Nobel Prize, and then pivoted his career almost entirely to the problem of the Hubble constant. He has calibrated the distance ladder rung by rung, checked every systematic error he could think of, used every new instrument that became available. He is one of the most decorated observational cosmologists alive, and he is spending his career on a number, on the difference between 67.4 and 73, on an 8% discrepancy that most people outside the field would not consider significant. He considers it significant because he understands what it implies. 8% in the Hubble constant at the precision now available is not a calibration uncertainty. It is a statement about the universe, about whether the universe we can see today is the universe that lambda CDM predicts should have evolved from the Big Bang. about whether something happened between the Big Bang and now that the model does not account for, about whether the picture we have assembled, with its dark matter and dark energy, and cosmological constant and cold initial conditions, and inflationary seeding, is the full story or an approximation to a deeper one. Rios believes it is an approximation. He has said so. He is careful about it. He caveats it. He acknowledges that systematic errors might still exist. But his reading of the evidence after more than a decade of measurement at the highest available precision is that new physics is required. He is not alone in this view. A 2024 review of the Hubble tension literature, summarizing the work of hundreds of researchers across dozens of independent measurement teams and theoretical proposals, concluded that systematic errors alone are unlikely to explain the full discrepancy. The tension is most likely cosmological in origin. Meanwhile, the JADES team at Webb, led by Nora Lutskendorf and Brant Robertson and Daniel Eisenstein, and many others across a large international collaboration, continues to conduct its deep field survey, cataloguing the earliest galaxies accessible to Webb's instruments, measuring their redshifts and stellar masses and star formation rates and chemical compositions. Every semester brings new data. Every new data release reveals more galaxies at higher redshifts, refines the mass estimates, adds to the statistical sample. The population of early massive galaxies is growing, not shrinking. These are real people doing real work, not in a vacuum, in conversation with the entire community of cosmologists and theoretical physicists who are watching the data accumulate and trying to build models that explain it. The conversation is global. It happens at conferences in Geneva and Pasadena and Tokyo and Cape Town. It happens in pre-print papers posted to Artif before peer review, where anyone can read the results within hours of them being written. It happens in real time, with a speed and openness that no previous generation of scientists experienced. This openness is itself part of why the anomalies are so well documented, because anyone can check the data, because multiple independent teams are analysing the same observations and arriving at the same tensions, because there is no shortage of motivated, careful researchers looking for errors in the results they find interesting, which is the best quality control science has ever invented. The crisis, if it is a crisis, is the most transparent and democratically documented crisis in the history of cosmology. Every step of the argument is public. Every measurement is citable. Every proposed solution is checkable. This is what distinguishes scientific uncertainty from ordinary uncertainty. The uncertainty is not about what anyone thinks or believes. It is about what the universe shows when you measure it carefully. And right now, the universe is showing something that the best model says it should not be showing. Quietly. Precisely. Without alarm. Without alarm is important. The tone in which this should be received is not panic. It is not even surprise in the sense of being caught off guard. The history of science predicts exactly this kind of situation. The history of science predicts that every very successful theory will eventually be found to be incomplete. That the incompleteness will first appear as a small persistent anomaly in a regime the theory was not originally developed to handle, and that the resolution will require a new and deeper framework that contains the old theory as a special case. That is the story of Newtonian mechanics and general relativity. That is the story of classical physics and quantum mechanics. That is the pattern. We are, in all probability, in the middle of the next iteration of that pattern. The framework is lambda CDM. The persistent anomalies are accumulating. The new data is coming. The resolution, when it comes, will almost certainly preserve everything that lambda CDM gets right, which is most things, while extending and correcting it in the regime where it is currently failing, which is the very early universe and the precise value of the expansion rate. What the resolution will look like, what the new physics will be, is the open question. And it is the most important open question in fundamental physics and cosmology today. The universe began 13.8 billion years ago. In the first fractions of a second, the laws of physics operated at energies so extreme that we have no tested theory to describe them. In the first 3 minutes, the light elements were forged in nuclear reactions we can calculate precisely. In the first 380,000 years, the universe was opaque plasma, and then it became transparent and released the light we now call the cosmic microwave background. In the first 100 million years, the first stars ignited in darkness we cannot yet directly observe. In the first billion years, the epoch that Webb is now illuminating, the first massive galaxies assembled by processes we do not yet fully understand. And in the 12.8 billion years since then, the universe continued to evolve, to build structure, to expand at a rate that two of our best measurement programs cannot agree on. You are made of atoms forged in stars that lived and died billions of years before the sun was born. You are the result of 13.8 billion years of cosmic history, expressed in a configuration of matter complex enough to ask questions about the universe that made it. You are sitting or lying in a room on a planet that is itself a very small and specific outcome of all of that history. And at the edge of the volume of space that your species can observe, at the limit of what light has had time to reach you from, there are galaxies so old and so unexpectedly massive that the story you have been using to describe the universe has to be revised to include them. That revision has not yet been written. It is being written now by the people running the instruments, running the simulations, writing the papers, checking the numbers. You will not have to wait 50 years for it. You will not have to wait 20. The data from Euclid and Rubin and Roman and the square kilometre array will determine the shape of the new story within the next decade. The next generation of cosmologists, many of whom are graduate students right now, calibrating instruments and writing analysis code and staying up late with datasets that no previous generation had access to, will be the ones who make the decisive measurements. What they will find, we cannot know. That is the nature of genuine discovery. If we knew what they would find, there would be no investigation. There would only be confirmation. But the fact that they will find something, that the investigation is structured, the questions are sharp, the instruments are capable, and the anomalies are real, that is confirmed. The investigation is ongoing. The universe is waiting. And at the very edge of what we can see, in light that has been travelling since before the solar system existed, something is telling us that the story we have been telling is not complete. We are getting close enough to hear it. There is a specific number that captures what is at stake in this investigation, and it is worth sitting with for a moment before continuing. The observable universe contains approximately 2 trillion galaxies. 2 trillion. The number is confirmed. It was published by a team led by Christopher Consellis in 2016, based on the accumulated deep field imaging from Hubble and ground-based telescopes. 2 trillion galaxies, each containing on average hundreds of billions of stars. The Milky Way alone contains an estimated 200 to 400 billion stars, each potentially orbited by planets, each a nuclear furnace converting hydrogen to helium at millions of degrees, each burning for millions or billions of years before exhausting its fuel and dying in ways that range from quiet collapses to explosions visible across the entire observable universe. The number 2 trillion galaxies is so large that the only useful thing to do with it is to not try to comprehend it as a number. Instead, consider what it implies about the process that produced them. All of that structure, all 2 trillion galaxies, all hundreds of billions of stars per galaxy, all assembled through the gravitational collapse of gas seeded by tiny quantum fluctuations in the first instance of cosmic time, had to form by rules. Rules of physics, rules of gravity, rules governing how energy density and matter interact across cosmic scales. Those rules are what lambda CDM describes. And if those rules are even slightly wrong, if the Hubble constant is 73 rather than 67.4, if the first galaxies grew 10 times faster than the simulations allow, then everything we think we understand about how 2 trillion galaxies came to exist is incomplete. Not wrong in its broad outline. The Big Bang still happened. Inflation still seeded the initial fluctuations. Dark matter still built the halos. Ordinary matter still fell in and formed stars. But the details, the timing, the efficiency, the dynamics are different from what we calculated. And those different details are a window into physics we have not yet discovered. That is what the impossible galaxies at the edge of the universe represent. Not an embarrassment, a window. Consider also what it means to have 2 independent methods of measuring the same quantity, the expansion rate of the universe, that persistently disagree. The Hubble constant, as measured from the early universe through the cosmic microwave background, is 67.4. As measured from the late universe through the cosmic distance ladder, it is 73. These 2 numbers describe the same universe. They should agree. The fact that they do not means that something about the universe's history between those 2 epochs, the 13.8 billion years from the Big Bang to now, is not captured by lambda CDM. Something happened, or something is present, or something has a value that the model assigns incorrectly. The universe does not make measurement errors. We make measurement errors. The universe simply is what it is. What the Hubble tension tells us is that the universe, when measured carefully by 2 completely independent methods using completely independent physics, gives 2 different answers. That means the model connecting those 2 measurements, lambda CDM, is missing something. Something that, when included, will reconcile the measurements and deepen our understanding of what the universe actually is. This is not a new situation in the history of science. Every major advance in our understanding of nature has come from exactly this kind of precise disagreement between 2 careful measurements, or between a precise prediction and a precise observation. The orbit of Mercury and general relativity, the ultraviolet catastrophe in blackbody radiation and quantum mechanics, the anomalous magnetic moment of the electron and quantum electrodynamics, the missing neutrino flux from the Sun and neutrino oscillations. In each case, a small, persistent, precise discrepancy between theory and observation was the thread that, when pulled, unraveled one framework and revealed a deeper one. The Hubble tension may be that thread. The impossible early galaxies may be that thread. Together, they may be the same thread, connected below the surface in a way that is not yet visible. And whoever finds the physics that explains them both, whoever publishes the paper that makes both numbers make sense simultaneously within a coherent framework, will have made one of the most important scientific discoveries of this century. That paper has not been published yet. The person who will write it may be a graduate student right now, working late, puzzling over datasets from Webb or from Euclid, noticing something that does not quite fit. This is where science lives. Not in the textbooks, which describe what is already known, not in the popular accounts, which describe what has already been settled. Science lives in the gap between what we know and what we can measure, in the precise moment when the measurement reveals something the theory did not predict. That gap is where the universe speaks most clearly, if you're quiet enough and careful enough to listen. Right now, the universe is speaking. It is speaking through the light of galaxies at the edge of what Webb can see, galaxies that the standard model forbids. It is speaking through the 8% disagreement between 2 of the best measurement programs in the history of observational astronomy. It is speaking through the subtle hint in DESY's data that dark energy may not be what we assumed. It is speaking with patience and precision and without urgency in the language of photons and redshifts and spectral lines and baryon acoustic oscillations. And we are, for the first time in history, building instruments delicate enough to understand what it is saying. What it is saying is this: the story is not over. The investigation is not complete. The picture is not finished. There is more. There has always been more. And now at last the tools exist to find it. The investigation is ongoing. The impossible galaxies are real. The tension is measured. The instruments are running. And the universe is patient. It has been waiting 13.8 billion years for a species to ask the right questions, with the right instruments at the right time. It will wait a little longer for the answer. We are almost there. There is one more thing, something about the specific strangeness of this investigation that gets lost when you list the anomalies one by one, as if they were items on a checklist. Something about the unified picture, the single coherent thing that all of these measurements in aggregate are trying to say. We built our model of the universe from the inside. We built it by looking out from a small planet, orbiting an average star in the outer disk of one of 2 trillion galaxies, and measuring the faint light of objects at the edge of what we can see. We took that light, broke it into its components, measured its redshift and its temperature and its chemical content, and from those measurements, we reconstructed the entire history of the cosmos from the first fraction of a second to the present day. We inferred the existence of dark matter and dark energy from the behavior of things we could see, even though we could not see dark matter or dark energy directly. We deduced the shape of the primordial density fluctuations from the pattern of temperature, variations in radiation that has been travelling for 13.8 billion years. We predicted the distribution of the lightest elements from nuclear physics operating in the first 3 minutes of cosmic time. All of this from a single planet, from instruments built over decades by limited numbers of people with limited resources, limited computing power, limited observing time. The fact that the model works as well as it does, that it predicts the CMB pattern, the large-scale structure, the element abundances, the existence of dark energy, is, when you step back and look at it clearly, almost miraculous in the non-supernatural sense, almost impossibly unlikely to have been achieved and yet achieved. And now, at the edge of what those instruments can reach, in the regime that was previously inaccessible, in the earliest epoch of galaxy formation, in the most precise measurements of the expansion rate, the model is showing small but persistent signs of strain. Small relative to the model's successes, but measurable, confirmed, real. The impossible galaxies at the edge of the universe are not a failure. They are the frontier. They are the place where the model meets its limit, not its total failure, but the edge of its validity. The place where it was never fully tested, where the data that would test it did not previously exist. Webb is providing that data now. Euclid and Rubin and Roman will provide more. And in that data, in that new frontier, is the next chapter of the most ambitious investigation in human history. You are here for the frontier. You are alive at the moment when the frontier opened. That is not nothing. That is, in fact, the most interesting place to be. The universe does not owe us an explanation. It does not arrange itself to be comprehensible. It does not slow down or simplify itself for the benefit of a species that has been asking questions about it for a few thousand years out of 13.8 billion. And yet, here we are, building telescopes, measuring redshifts, finding the impossible, asking what it means. That is the investigation. It is ongoing, it is real. And somewhere at the edge of what we can see, in light that has been travelling since before the stars of our galaxy were born, the answer is waiting. We are going to find it.